Good evening, everybody, to the participants from India, and yeah, and good morning to other participants from Europe and America. Yeah, hello, Professor Isabel. Yeah, I hope you are doing well. Yeah. Okay. Good evening, everybody.
Hello,
To the participants from India, and yeah. Okay. Okay, so now we have our first speaker. So before we introduce our speaker to all the participants, I would like to introduce this particular short-term course and what it is all about. Then give a short introduction. Then we can start. So this short-term course, which is starting today, it will. It is 4 days duration. It will focus on green solvents, such as this Eutectic solvents and Ionic liquids. And this particular short-term course is devoted to 3 different applications. The first part, Professor Isabel will be taking up the solvents, these Eutectic solvents and Ionic liquids for applications such as in pharmaceuticals on wastewater. While in the second part, we will be talking more about the microfabrication part, which includes the separation of this endocrine disrupting chemicals, and some discussion on the quantum chemical and molecular modeling strategies for the remediation of these micropollutants. And the last part will be conducted by Professor Bernardo from Brazil. So he will be discussing lectures regarding its application towards biomass, the strategies towards the extraction of bioactive compounds or the processing of biomass, organocatalysis, and finally the integration with environment. So the sponsor, I should be naming the sponsor. This is the sponsor is our government. Now it is called renamed as the Ministry of Education. So the scheme for promotion of academic and research collaboration is called the SPARK, which is aims at improving the research ecosystem of Indian higher education system by facilitating academic and research exchange with the best institution in the world. So this current workshop is actually an outcome between University Nova de Lisboa from Portugal, our own institute, Indian Institute of Technology, Guwahati, and Federal University of Rio de Janeiro, Brazil. So this was a short introduction or what you want to expect from this particular short-term course. Now I would like to introduce the speaker, Professor Isabel M. Maruco. So Professor Maruco obtained a PhD in chemical engineering from Instituto Superior Tecnio and from Colorado School of Mines in 1997. She is current professor at Instituto Superior Técnico at University de Lisboa, and her research interests are centered on green and sustainable chemistry, in particular the study of ionic liquids and Eutectic solvents and their application to develop separation processes. So now I will request Professor Maruco to start. Then I'll again like to thank her for accepting this request and particularly short-term course. And yes, now I will invite her to continue and start his own lecture. His first lecture is titled on ionic liquids and Eutectic solvents as alternative solvents. So, Professor Maruco, would you like that they ask question in between, or they will ask the question at the end of the lecture? Whichever way you agree.
Anything for me is fine. I mean, but perhaps it is better if they ask in the end, because I cannot see all participants, and if they raise the hand, probably I will not be able to see them. However, if they want to ask questions in between, it's fine for me also.
Okay, so maybe what we can do is that we at the end we will be better to be at the end. Else they can put their question in the chat box, and we will take up this question at the end of the lecture. That will be fine.
Yes, that's great.
Okay, fine, great. So yeah, so then once again I welcome Professor Maruco, and I will invite her to start her lecture.
Can I share my presentation?
Are you using the app or you are using the browser? It has started. Yeah.
Okay.
Yes, we are able to see.
Yes, yes.
Yes.
Is everybody able to see my screen? Okay, hopefully yes, because I cannot see you. I'm in presentation mode, so I cannot see anybody. Okay, so good afternoon to everybody. My name is Isabel Marrucho, and first of all, I would like to thank Professor Tamal for this kind invitation to give this short course, to participate in this short course. That our joint project, the Spark project, gently financed. So the title of my presentation today is Ionic Liquids and Eutectic Solvents. And I'm going to focus on two efficient approaches first for water treatment and then for vaccine production. So what I'm going to talk to you about today is a little bit about ionic liquids and eutectic solvents. I'm going to go a little bit in detail in their structure and how they behave as fluid phases, compare them, and then to show you some applications on water, on products that are in water. Okay, so this is a street walk in Lisbon, and it is in one of our main squares, and you can see here the world map. So here is Portugal, and I believe that you guys are in here. So this is a little bit like the trip that Vasco da Gama did, the first one, when he discovered the maritime way to India. Vasco da Gama was one of our Portuguese sailors that in the 16th century discovered the maritime way to India. So it was at that time, it was very difficult to discover because they had to go around here, Africa. They could not go through the red line, they had to go through the green line. And so it was one of our trips, discovered the new world, and we ended in Calcutta. I guess, I don't know how you say it. These are some photos from Portugal. I'm sure that all of you know about Algarve and the beautiful beaches that Algarve has. Right now, we are also very well known because of our surf waves. So this is in the south of Portugal, and this is in the Atlantic coast. You can see that this is a giant wave that is more than 50 meters of height, and you can see here a surfer. Okay, we also have castles. This is one of the most beautiful castles in Europe. It's nearby Lisbon. So this is Lisbon, this is Sintra, where this castle is. And it is very well known all over the world because of its bright colors. And here you can also see the grapes from the port wine grapes. And this is the port wine region. And the way that the vineyards are put along the Douro Valley that is considered World Heritage. Okay, so we come back to Lisbon, and this is where I work. This is Instituto Superior Técnico, which is the engineering school of the University of Lisbon. So Instituto Superior Técnico is this, and we work here in the South Tower. This institute was founded in the 20th century, in the beginning of the 20th century. Right now it has around 11 students enrolled, and we have more than 50 programs altogether, undergraduate, master, and PhD programs in engineering. We are an engineering school. So this is the South Tower, the chemical engineering tower, and this is several photos from my group, the extraction and separation technologies group. Okay, so as I promised to you, I'm going to talk about ionic liquids. First, I'm going to talk about ionic liquids, then I will talk a little bit about eutectic solvents. So ionic liquids, as you all know, are organic salts that are defined that they are liquid below a conventional temperature of 100 degrees C. And as they are salts, they are formed by one cation and one anion, typically an organic cation and an inorganic or organic anion. So what is the difference between ionic liquid and a common salt? As you can see here, I have this temperature scale, this thermometer, and I put there the melting temperature of sodium chloride, which is around 800 degrees C. So what we get when we replace the sodium salt by an imidazolium is 700 degrees in the melting point. So the melting point of C2-mine chloride is 79 degrees C compared to the sodium chloride that is 800. I can even decrease more the melting point of this ionic liquid just by increasing the size of the cation. So if this chain here, instead of an ethyl, it becomes an hexyl, the melting temperature is minus 37 degrees C. This imidazolium cation is the most iconic cation in the ionic liquid chemistry toolbox. How does this happen? How do I get such different melting points? You can see here that the structure is very different from the sodium chloride that is very nicely packed crystalline structure to an ionic liquid that is a disorganized liquid structure. Even when it is solid, it is much more disorganized than that of sodium chloride. So it is exactly that, is the difference in the symmetry of the anions that increases the entropy and makes the ionic liquids liquid at room temperature. So here we can compare at room temperature sodium chloride and imidazolium NTF2, and the difference between these two salts, let's say, you can see it here. The sodium chloride is very symmetric, and the C2-mine NTF2 is both cation and anion are quite asymmetric. So they do not pack in a crystalline network, and so they become liquid. Okay. This slide is a slide that I have been using for quite some time on the cations and the anions that are available in the ionic liquid toolbox. And today, before this presentation, I decided to freshen up my slide. And although some other cations and anions have been proposed, pretty much everything stayed the same. So we have a couple of main groups of cations and a couple of main groups of anions, and then we can do derivations, increase the alkyl side chains, instead of being an alkyl, being an ether, you name it. And so this is how we diversify between cations and anions. So we can make so many cations and anions that their combinations are over 10 to the power of 6 cations and anions combination. And although some authors say that this is a true advantage, that we can always pick one cation and combine it with a very different anion, the fact is that then it is very hard to choose where do I start my experiments, where do I start my simulations, how should I pick a cation and an anion for a specific purpose. In general, ionic liquids are said to have a wide liquid temperature range. So you can see here, and as I showed you before, that some ionic liquids have a melting point below room temperature. They have a wide electrochemical window. They have negligible vapor pressures. And because of this important property, they have been considered green solvents in the beginning, because they are totally different from organic compounds that are volatile, and they create all the VOC problems that we have today. However, keep in mind that not all ionic liquids are green, because being green does not only mean that they have negligible vapor pressure, it also means that they are biocompatible and biodegradable, and some of our ionic liquids for sure do not fulfill these properties. Also, a very important property of ionic liquids, some of them, is their high thermal stability. So when we use fluorine and ions, we can have stabilities that go up to 200 degrees C, 250 degrees C. However, if we choose, for example, the acetate anion, we know that the thermal stability is going to be much lower. So these are properties that we have to keep in mind when we select our ionic liquids. In general, they are non-flammable. And a very important property of all ionic liquids is the high solvation ability and coordination properties, meaning that ionic liquids brought for the first time the Coulombic interactions to solvents. When we think about organic solvents, they have hydrogen bonds, they have van der Waals interactions, but never they had Coulombic interactions. So ionic liquids offer us huge tunability of the solvation. There is ionic liquids that are toxic, that are those that are non-toxic, that are those that are in fact medicinal properties or antifungal. And one anion. Okay, so here I have I have a polarity scale, which is a very important property of ionic liquids. When we mix ionic liquids, for example, with other solvents, I have here water and I have here ethane, and these profiles were taken from, they are charge density profiles, and they were taken from Cosmos program. And we can see here that they are very different, the profiles for water and ethane. And so we need to find among ionic liquids, profiles that match both of these two solvents. And we can see that we can have ionic liquids that are very, very apolar or non-polar, like this benim. And we can see that we can go all through the way in the polarity scale to the chloride anion. And so we have a very polar ionic liquid, at least in the anion part. So we can really tune the properties, the solvation properties that I was talking about. In fact, in this figure, we can see a very interesting thing. I was talking about that we have, for the first time, with ionic liquids, we have for the first time Coulombic interactions in solvents. Here in this graph, I have represented the Coulombic interactions in red and the van der Waals interactions in green. And what we can see is that there are, in fact, ionic liquids that have higher van der Waals interactions than Coulombic interactions. That is the case, for example, of these phosphonium-based ionic liquids combined with fluorinated anions. You can see here that I can have very non-polar solvents that probably are very good for the extraction of, for instance, ethane. as we were talking about here in this previous slide. However, when we talk about something to be mixable with water, I need to choose an ionic liquid that has a very high Coulombic part or a very high hydrogen bonding part that is not represented here. And probably I would choose this one here that is the C4 bimine, but combined with the acetate. So this gives you an idea about the extraordinary capacity of tuning ionic liquids properties. Just by combining different ions with different cations. So let's see a little bit of the structural organization of ionic liquids. For instance, if we again pick up the dialkylimidazolium salts, we know that they have an extended networks of cations and anions all connected together by hydrogen bonds. And this is a very simplified solid state model. However, it has been shown that ionic liquids, either in the solid, in the liquid, and in the gas phase, are, of course, not as organized. They have some degree of organization. So they are more organized than organic solvents, and probably this is due to the strong interactions between the cations and the anions. For example, we can see here in this picture the introduction of some other molecules, polar molecules, and we can see that we have structure between the cations and the anions. The other salts that we have that behave similar to these are surfactants. So in fact, if you think about this, ionic liquids are very similar to surfactants in terms of structure because they really organize themselves with the non-polar long hydrophobic chain all together, so on one side, and the polar parts, so the polar head of the surfactant, the sulfate group, with the sodium here on the other part. This was shown for the first time in MD simulations quite some time ago. And these simulations were done by two Portuguese people. One of them is from my institution, Canonge Lopes, and the other one is a researcher in France, Gilles Padua. And they showed for the first time the separation that exists and the structure of ionic liquids. So they started with C2-mine PF6. And here you can see the color code, so the cations and the anions. The anions are in red and the cations are in green. And we can see that as the chain, the alkyl chain of the imidazolium grows, there is more green in the box, but the green is not all spread around. So the green is all together, which means that the polar chains in ionic liquids segregate. So they form domains, just like in surfactants. So this is very interesting, and we can take advantage of this nanostructural organization of ionic liquids. This was a very important paper, the fact that they showed that the ionic liquids are nanostructured. Here we can see better the non-polar domains. So they just removed all the charged parts of the ionic liquid. And we can see here as the alkyl chain increases, the hydrophobic domains increase, but they are not spread around. They are all connected together. What does this bring? This brings important properties in terms of solvation. For example, in this slide here, I'm showing the interaction of N-hexane, acetonitrile, and methanol with bimine PF6. So the alkane is located in the non-polar domain, and here we can see that very well, that the alkane, the N-hexane, dissolves in the non-polar part. Here in the acetonitrile, we can also see that the acetonitrile is balanced between the green and the red. And here in this third part, we have the methanol. And the methanol established, so it has a NOH group, and so it establishes strong interactions with the anion, much stronger than with the cation. And so we can see here that the methanol preferentially establishes interactions with the cation instead of the anion. So here on the first examples, I talked about polar domains and non-polar domains, while here in this third example, I talk about more direct interactions with either the cation or the anion. And so you can see that we can really tune the properties of our solvents just by playing around with the alkyl side chains in the cation, in the anion, and sometimes by introducing groups such as the OH group or the anether group, etc. Oh, I've shown this before. Okay. So ionic liquids are green solvents. Ionic liquids belong to the group of green solvents. This is why ionic liquids are so important. And so we need to understand what are the difference between ionic liquids and the other green solvents. In this table, I have a comparison with ionic liquids and other green solvents, such as supercritical CO2, fluorous solvents, water, and bio-based solvents. Generally, we can see that we have here the key properties of ionic liquids are they are designer solvents. So they can we can tune the properties of ionic liquids for a specific application. It's like our slot machine. Then, in terms of easy separation and reuse, we can see that the volatile products can be easily removed. However, the other products that are soluble in the ionic liquid cannot be easily removed. And this is probably one of the important points. That's why it makes ionic liquids so expensive, is that they are difficult to purify. And so ionic liquids still today are expensive. Expensive, okay. In terms of health and safety, as they are so diversified, there are ionic liquids that are in fact biocompatible and non-toxic. However, there are other ionic liquids that are very toxic and very flammable. So we need to avoid generalizations. In terms of cradle to grave environmental impact, they are typically, and still today, most of them, synthesized from petroleum-based chemicals. But as time goes by, more and more ionic liquids are being synthesized from renewable resources. And so here you see, compared to the other solvents, you see that they would give a very good score, in fact, to ionic liquids, 13, which is one of the, so in up to 25, they give a score of 13, probably because they are expensive and probably because they are difficult to synthesize. Okay. Realize, however, that we have here water, but water is really much more environmentally friendly than ionic liquids, but with water, I can extract polar compounds. Supercritical CO2 is much more environmental friendly than ionic liquids, but with supercritical CO2, I can extract polar compounds. So really, there is not a class of solvents that offers the tunability that ionic liquids offer. Okay, here I have also a table that compares ionic liquids with other organic solvents. And what you can see is that if I want to choose, I have here 10 to the power of 6, 1 million ionic liquids available, while in organic solvents I have 1,000, okay? I have here the negligible vapor pressure, the multifunctional. The polarity concept is a little bit questionable, and it started to be questionable when the ionic liquids were found to be nanostructured, because I cannot say that overall an ionic liquid is polar or non-polar because it is nanostructured. However, here also they are designer solvents. And so I think that this is the way to go. If you need to tune something, if you have to have a specific property for an application, you have to go with ionic liquids. Ionic liquids over the years, we can see that they are still growing up. Per year, there is something like 10,000 publications on ionic liquids, still growing up. And what we can see here, and I took this from the Easy Web of Knowledge yesterday, what we can see here that still we have a lot of characterization, but and the characterization and materials development, but now we are going more over to the chemistry applications, the chemical engineering, a lot on electrochemistry also, and energy and fuels and analytical chemistry. So these are the areas where papers are published. Let's see if they match the areas where people that produce ionic liquids think that they are used. So in terms of the curve that I showed you, there is in literature, there is this curve that is called the hype cycle, and that says that all the novelties go through this hype cycle. So they have they have a phase where the expectations are really high, they are going up, and then they are really high, they are at the peak. We think that they are going to save chemistry and chemical engineering and science in general from everything. And then we started to see the drawbacks. And then we started to think that it cannot be used. We start to know the failures of our solvents. Everything pretty much falls apart. However, then a second generation of products, much more intelligently adapted, are starting to come up. And methodologies are being used to deal with this second generation of products. And the expectations start picking up until we have a consolidated experience and we can use them in a productive way. So this happens with all novelties, and everybody is asking, where are we? I do believe that we are already here in this phase, climbing the slope. So the 90s and the beginning of the 2000th century were this part. Then there was 10 years where everybody was quite disappointed with ionic liquids, and this is where deep eutectic solvents came through. But now I think that some ionic liquids are really important for some applications, and we'll see in a bit. And we are here climbing the slope to the plateau. Okay, so let's see what 3 companies that produce ionic liquids say about them. So in the page of Iolitech, and also I took them this yesterday, they think that they are big in analytics, electrochemistry, energy, and they will also be important in separation area, synthesis and catalysis, and functional additives. Additives is a really important point because ionic liquids are expensive. So this is a major producer of ionic liquids. The other one is Solvionic. And Solvionic says that the future of ionic liquids lies again in energy storage, catalysis, analytical, separation and extraction, surface treatment, and biotechnology. Realize that biotechnology was not in the Iolitech panoply of applications, but I do think that ionic liquids are going to be very important in biomass conversion and protein purification. The third producer of and commercializer of ionic liquids is Sigma-Aldrich. This used to be Merck, and Merck was bought by Sigma-Aldrich. And so Sigma-Aldrich thinks that they are going to be used in electrolytes, in separation as electroelastic materials. This is new. Analyticals also, biosolvents, lubricants, and additives. So each one of our companies thinks that they are used, the producers think that they can find interesting applications in these areas. Some have one different area, but pretty much they all agree on the areas that they are used. If you talk to somebody that does process engineering and you say that you're working on ionic liquids, they will laugh at you and they will say that you'll never be beyond the lab stage. This is really not true. There are a lot of companies that are already working with ionic liquids and that use large amounts of ionic liquids. Everybody knows the process, the acid scavenging process by BASF, and all these other processes that we have here on fluorination, electroplating, etc. So how can all these applications deal with such expensive solvents? I mean, if an ionic liquid flask is 200 euros, I'm sorry, how can these companies cope with these prices? First of all, it's 200 euros for us who buys them. Second, all these companies produce their own ionic liquids for their specific applications. And third, the key to use ionic liquids is really to have a cyclic process. A cyclic is really to recycle the ionic liquids and reuse it, because as we've seen, ionic liquids are very stable, and so we can take advantage of that. This book by Professor Mark Shiflett just came out. Professor Mark Shiflett has a very good understanding of what's going on in industry. He was in DuPont for a lot of time, for a lot of years, and now he just moved into the university, and he wrote about commercial applications of ionic liquids. So if you're interested in commercial applications and in industry, you really need to take a look at this book. It is very interesting. Okay. In terms of classification, there are a lot of classifications for ionic liquids, but I still like the first classification that was proposed. So this was the first generation of ionic liquids, when we were still trying to tune the ionic liquids properties in order to check which was the density or the viscosity of the ionic liquids. And now we are no longer in the first generation of ionic liquids, because now we know that we can tune them, and sometimes we need to tune them for specific applications. But right now, we have already gone to this second generation. And the second generation comes from knowing what ionic liquids are and characterizing ionic liquids to developing processes and products and materials with these ionic liquids. So you can see that slight changes in the chemical structures were made in order to fulfill some of the applications that are envisaged. For instance, if we want a high density energy, or if you wanted to have an electrochemical window, so we need to find something that really is small and conducts. The third generation of ionic liquid are the ionic liquids that have biological properties. This has also been explored, and right now it is being explored enormously. It is known that ionic liquids, that pharmaceuticals can be formulated as salts. And so right now, pharmaceuticals can be formulated as liquids just by the use of a cation or an anion that is an ionic liquid. Okay. So how, for some applications, it is quite important to understand the difference between ionic liquids and molten salts. And so I have here this scheme where ionic liquids, where molten salts are like these small round molecules, cations and anions, that are all spheric and have coulombic interactions that are radial. However, when we go to an ionic liquid, we've seen that these spheric ions, either cations or anions, are no longer present. And so ionic liquid begins to behave more like Lego pieces. And in Lego pieces, the interactions are very different. So we have Coulombic interactions, but then as we have also to match like the pieces, like in a Lego puzzle, we start to have directional interactions, which are the hydrogen bonds. Everybody knows that hydrogen bonds are very important in ionic liquids. That cations and anions can interact through Coulombic interactions, but there are and anions that really interact through hydrogen bonds. Another very important property that we also need to keep in mind is how close together is an ionic pair connected to each other. For instance, right now, when I was preparing to give this talk yesterday, I was browsing through literature, and they say that we have neutral ionic liquids if the cation and the anion do not have an intimate interaction. Here in this work, the interaction between the cation and the anion was evaluated as a function of the anion. For example, we can see that the chloride anion is much more binding, is much more able to form aggregates than the NTF2 anion. Why? Because the charge in the NTF2 anion is much more, is not as localized, so it's more delocalized. And this anion is particularly very flexible, which means that if I'm going to study an ionic liquid that has the NTF2 anion, for example, for electrochemical applications, this would be a good choice because the cation and the anion are relatively free and they can move around easily. Okay, this is exactly what I was telling you about. So this here is the chloride with high energy interactions. And these are some fluorinated anions like the FAP, the NTF2 anions that are large, complex, and they have localized or shield charge. And so this is very useful for us to know if we want our ionic liquid to have, to have free charges, or if we want it to have like a more non-polar character. What we can see here also is that the binding energy of a cation or an anion can also be correlated with its hydrogen bonding. Of course, if we have something like an anion like acetate, the part of acetate will bind through hydrogen bonding with its cation. For example, here in the imidazolium cation in the acidic hydrogen. Okay, here is what I was telling you about. So this interaction here is an acidic interaction. And so this is a thing that we need to keep in mind when we think about the specific application. So this binding between the cation and the anion has also been put using the concept of ionicity. And ionicity is a concept that is usually measured through a Walden plot. And we have here a Walden plot. Walden plot is a log-log plot of the conductivity versus the fluidity. And what we want good ionic liquids, so we want them to be highly conductive and fluid. And the poor ionic liquids will be here in this side of this conventional line. This line is for our electrolyte. It's the Walden electrolyte, which is KCl, sodium chloride, at the concentration in water, at the concentration of 0.1 molar. Okay, so what does ionicity truly mean? Okay, what ionicity truly means is that I don't have very directional interactions. So here, the chloride is very close to the sodium, but in here, they are not very bound together, so are relatively free, and the anions and the cations can move around. This is also a very important property to evaluate when we think about applications that need electrical conduction. Okay, so let's talk now about the problem that in that downwards phase that I showed you before. One of the big problems when we synthesize ionic liquids is that sometimes we tune and then when we prepare them, they are solid. They are not liquid. And this happened, for example, with the choline chloride. Choline chloride was started to be used around in the year 2000. And choline chloride is part of the vitamin B complex. And so it was the first ionic liquid that was biocompatible. However, it cannot be used as a solid because it is solid. It cannot be used as a solvent because it is solid. So what can we do? How can we solve this problem? Another disadvantages of the ionic liquids are here in this table. So I have here the advantages and the disadvantages. In terms of the disadvantages, as you can see, it's the cost. They are expensive. They are very viscous. They have low vapor pressure. And low vapor pressure can be an advantage because it means that it does not contribute to the atmosphere emissions, or it can be a disadvantage because it means that I cannot use distillation to carry out separations. The synthesis is complex. The sustainability, it really depends on what we try to synthesize. We've seen that some that we can prepare them from renewable resources and the others not. Hygroscopicity, some are hygroscopic and they are corrosive. This is a true problem in ionic liquids. However, they've also a lot of advantages. The main advantages is again the fact that they are designer solvents. So we can combine 10 to the power of 8 cations and anions to generate a huge amount of solvents that I can choose from. They are non-flammable. This is very important for a wide variety of applications. They can also be used, I mean, I can evaporate the compounds or I can evaporate impurities, so they can be easily separated through vapor-liquid equilibrium. And they are very thermostable. So as you see, as in all things, we have problems, we have advantages and disadvantages. The fact is that when we were at this point, in 2004, Abbott proposed the use of a formation of eutectics to have solvents, liquid solvents at room temperature from choline chloride. So what he did is he combined choline chloride with urea, for example. And this is the solid liquid phase diagram. And what he verified was that at the composition of 1 to 3, that the melting point dropped considerably. There was a drop in melting point of 178 degrees C. And this is a very simple approach. So I just have choline chloride, I have urea, and they are both solid at room temperature. I heat them up and they become liquid. This idea of having of using the eutectic point of some mixtures of compounds enables us to prepare a huge amount of mixtures, so a large number of eutectics, without no need of purification because I just mix them, heat them, and they are liquid. And this is a very easy preparation compared to the ionic liquids that have typically impurities and they are very difficult to purify. And so this was how deep eutectic solvents were just said to be much better than ionic liquids. Of course, that the deep comes from the deep decrease in the melting point temperature. I would propose 4 families of deep eutectic solvents, and you can see that 3 of them use metals, and only 1 uses all organic compounds. And so these 3 have been, so type 1, type 2, and type 4 have been quite used in electroplating and energy applications. But the one that is the true winner in terms of solvents is this 3rd class of eutectics. Realize that for a while, people thought that eutectics were the same thing as ionic liquids. Eutectics are not the same thing as ionic liquids. Eutectics are mixtures of compounds, of 2 compounds. And also in the literature, there are people that say that we have a special complex here at the eutectic point. We do not have any complex when we form eutectic mixtures. We just have, in some proportions, that we have a larger deviation from ideality than in the other proportions. So what we have here, what we take advantage is this increased liquid region, homogeneous liquid region. This is where eutectic mixtures work. So how do I prepare eutectic mixtures? Are they easy to prepare? They are very easy to prepare. However, they can also be sold. There are people that are selling these. In our lab, what we do, our most the way that we prefer to use is just by heating the 2 compounds together and then cool them down slowly to room temperature. There are also other ways to prepare the deep eutectic solvents, which is put the 2 solids inside of a flask, add water, mix well, and then evaporate the water. When you evaporate the water, you also get the liquid. The 3rd way of preparing eutectic solvents is by grinding. The grinding method, so you just put the 2 compounds, solid compounds, and you ground it until you get a liquid. These 2 last forms of preparing deep eutectic solvents avoid the decomposition of some compounds that are not thermally stable, like for instance, acid. And so sometimes these 2 forms are preferred to this one. We really need to think about what we're doing. However, this 2nd form, the addition of water, because it's typically what it is added, also complicates very much matters. Because there are some water that stays inside of the eutectic solvent as residual water. And sometimes the properties that we get from this preparation is not exactly the same as the properties that we get from the other 2. And here it is, what I was telling you about. So sometimes when we use the heating method, and here we used for choline chloride and the acid, we saw when we used the heating method that the decomposition compound was here present. It was an ester. And here, when we use the grinding method, no impurity was present. So in these cases, it is preferable here or more impurities. So in these cases, it's preferable to use either the grinding or the addition of water instead of the heating method. So are there as many deep eutectic solvents as there are ionic liquids? I would say yes. This is a table of the organic salts that we can use and the hydrogen bond donors. And this is also a small table just I had before for the ionic liquids, because there are many, many more members of this table, hydrogen bond donors and hydrogen bond acceptors. And this is the key in deep eutectic solvents. If when we think about ionic liquids, we think about coulombic interactions and then hydrogen bond interactions. If we have cations and anions that can hydrogen bonds, here it has been shown that this is a truly alphabet soup, as Tom Welton called, because we have an intricate network of hydrogen bonds, and hydrogen bonds are really the most important bonds in eutectic solvents, at least in deep eutectic solvents. So I'm saying that we have deep eutectic solvents, but this implies that I need to classify deep. How deep is deep? How deep is deep enough? Abbott just got to 178 degrees C in the decreasing of the melting point. But there are a lot of deep eutectic solvents in literature, and I'm going to show them to you in a bit, that do not have this very large decrease. For instance, in this graph here, I have the experimental data, and this is the modeling with non-ideal data, with the ideal model, and this is the average between the two melting points. So as you can see, if I take the average between these two melting points, I have a large depression, but if I take deviation from the ideal mixture, I have a lower deepness of in the melting temperature. So what was defined is that deep eutectic solvents, and when I use deep, it means that I'm talking about non-ideal mixtures, so that I have deviations from the ideal mixture behavior. The others are called just eutectic solvents, eutectic mixtures, and we do not use deep. However, in order to know if it's deep or not deep, I need to come to the lab and measure the solid-liquid equilibria for all the deep eutectic solvents or the eutectic solvents that I am using. Only then I know if my eutectic is deep or not deep. Does deep matter? So we have to keep in mind that deep matters because a non-ionic mixture is a mixture that has more potential in terms of what it can bring to you than an ideal mixture. However, when we think about, oh, I had choline chloride that I wanted to use and it is solid and I really wanted to use it, but I need a liquid, the deep does not really matter that much. For example, I have here in this graph two non-deep eutectic solvents. And here I did not do I could not even represent the ideal behavior because I do not have the melting enthalpy of this salt here. So here, what I can tell you is that this is what I gain in terms of operation window when I perform the deep eutectic solvents. So if it's deep or not deep, it's really a question for the correctness, the thermodynamic correctness of what we are saying. And we shouldn't say it is deep when we do not know. But these eutectic mixtures are very interesting, especially because they allow you to use compounds that you could not use before. Okay. Water is also a very important property that we need to think about. For example, I showed you the table before, and in the table it said that one of the disadvantages of ionic liquids was the hygroscopicity. Let me tell you, deep eutectic solvents are much more hygroscopic than ionic liquids. And so we really need to think about what is the role of water in these deep eutectic solvents. For instance, we have here in this graph, in this other side, the effect of water on viscosity. As you can see, I have here different deep eutectic solvents. And for instance, in all of them, I took the water out as much as I could. They were in our vacuum line for a week. And in the choline chloride fructose, I still have 10 weight% of water, while for instance in glycerol, I only have 0.13 or in urea 0.1 weight% of water. So water is really a problem, especially when we do not know how it interferes with the structure of our deep eutectic solvents. What it has been shown and we've also done this. We've analyzed in FTIR some hydrogen bonds, the hydrogen bonding between the hydrogen bond donor and the hydrogen bond acceptor. And what we found with the composition of water, and what we found is that here in the beginning, for very short amounts of water, the water activity, that means the connection of the water inside of a dipiotetic solvent, does not very much change, but then it changes a lot as I put more water inside of my dipiotetic solvent. And this is as if I had 3 different regimes. Here it does not change very much. Here it starts changing, and here it changes a lot. And for this one, also we can find 3 regimes. This has been studied by several authors, including using molecular dynamic simulations. And they also found these 3 regimes, meaning that we can use some water for a very short amount of water, up to 5% of water, and the hydrogen bonds still are pretty much the same. Then there is a second regime where the hydrogen bonds starting to really change. So the water is really breaking hydrogen bonds and making other hydrogen bonds. And here in this regime, so over 30% of water where everything behaves differently. This is very important, especially because some authors put water inside of the dipiotetic solvents, because dipiotetic solvents can be very viscous and they can be useless if you don't use a little bit of water. For example, I'm going to give you an example of a dipiotetic solvent that you all know, which is honey. Honey is in fact a dipiotetic solvent between sugars. However, you don't even think about using honey as a solvent because of its viscosity. Nevertheless, if you go home and put enough water inside of the honey, honey will become less viscous. Heat it up, cool it down, honey will become less viscous, and it will be a good solvent. But what are the properties of this honey with water? This is where we need to be careful. Okay, so now I'm going to talk to you about other eutectic solvents that have been proposed, and then they are very popular, which are the natural eutectic solvents. They have been called natural dipiotetic solvents, and people know them by the name NADs. Okay, and they are composed of all natural compounds, sugars, amines, organic acids, alcohols, all natural compounds from renewable resources, all green. You can see here that for different compositions, we have some are liquid, some are solid. These are very immiscible with water, very hygroscopic, and very viscous, that I was telling you, like the honey case, if I put the sugar and the sugar. However, these are fully biocompatible and non-toxic, and so these natural dipiotetic solvents have a lot of advantages. In order to use them, as I was telling you, some authors even say that we need to have water. And they have explicitly water in the composition of the eutectics. For instance, this one here that has succinic acid, choline chloride, and water 1 to 1 to 1. So this is in a molar ratio of 30% of water. So this is a lot of water. Sometimes people report the amount of water in terms of weight percent of water. And 3 weight percent of water inside of a dipiotetic solvent is typically 35% molar of water. So it is here again in this range of 30% of water. So this falls here in this region or in this region where very few properties of my dipiotetic solvent are still together. So the dipiotetic solvent is like a mixture of sugars and water. What about vapor pressure? We have been measuring vapor pressure in our lab, and here you can see a comparison between some vapor pressure of some ionic liquids and the vapor pressure of some dipyotetic solvents. We should be tempted to say that all of them have very low vapor pressure. Typically, dipyotetic solvents are said to have very low vapor pressure. We have here, you cannot see it very well, but for example, we have here 29, the trig line, which is here 29, is higher than all the other vapor pressures. And then when we formulated it in dipyotetic solvent, like here in the 30, we really have a decrease in the vapor pressure of the dipyotetic solvent. We've also done it, and we've done it for a dipyotetic solvent made of sulfolane and tetrabutyl ammonium bromide and tetrabutyl ammonium phosphide salts. And we compare it also with the dipyotetic solvent with the pure sulfolane. And as you can see, and it is reported, is that dipyotetic solvent vapor pressure are around 80 pascals. And so 80 pascals is not bad, but it is not that low compared to ionic liquids that have like 1 or 2 pascals. And it is not that low compared to this parent compound. So in my opinion, not all dipyotetic solvents have low vapor pressure. It really depends on what you are doing, what compounds you are using. Here in sulfolane, we decrease for half of the vapor pressure. Okay. So here is a comparison of the ionic liquids and the dipyotetic solvents that I made for you. So what do you need to keep in mind? You need to keep in mind that ionic liquids are pure compounds and dipyotetic solvents are mixtures. And so they can separate. We are going to see how they separate. Right now, we have a very good knowledge of ionic liquids properties. We can predict very well some ionic liquids properties, such as density, viscosity. So if we need to if we want to synthesize an ionic liquid and if we want to have a grasp of the viscosity, we can do it. In dipyotetic solvents, that is not the case. Everything that is reported very much on the application side, and so most of the times is not very well characterized. And the fact that they are non-ideal mixtures still complicates a little bit more the prediction, because then we don't know which mixing rule works for what. Ionic liquids have very low vapor pressure, that's true. And as we saw before, this can be an advantage and a disadvantage. We have to keep in mind that dipyotetic solvents do not have that low vapor pressure, as low as ionic liquids, as it is usually written in papers. We have to think that the decrease in vapor pressure by the addition of a salt to a solvent is a colligative property. And so we need to think in this line of reason and not just to say that because they are like cousins of ionic liquids, they have salts in their constitution, that they will have vanishing vapor pressure. The ionic liquids can be toxic. For instance, there is the imidazolium that is the most iconic cation, as I told you, that is toxic. These can be non-toxic. They are typically, if they are made of selenium chloride, they will be non-toxic. If they are made of natural compounds, they will be non-toxic. So let's say that they are more non-toxic dipyotetic solvents than there are non-toxic ionic liquids. A great advantage is that ionic liquids are still expensive and dipyotetic solvents are cheap. They are, in fact, much cheaper than ionic liquids. Another advantage is that in ionic liquids, it's difficult to purify. And so impurities sometimes play a role in some of the properties. Dipyotetic solvents, if you're careful with temperature, they are pure. They're just mixtures. You don't do reaction. That's why when people say that they synthesize ionic liquids, in fact, they prepare ionic liquids. They do not synthesize them. And we need to think that they are very hygroscopic, much more hygroscopic than ionic liquids, and very viscous, much more viscous than ionic liquids. Okay. So this is the end of my comparison between ionic liquids and deep eutectic solvents. I don't know if now you want to make some questions before I go in and show you how these solvents can be used for extractions.
Yeah, so there are some questions. Professor Isabel, shall I ask on behalf of them? Is it fine?
Yes, it is fine. I mean, I can stop sharing just to
okay, fine.
See you,
fine.
But you can ask. Yeah, you can ask the question.
Yes. So there are participants from this this Teams links as well as YouTube. In YouTube, there is this participant Sunita Rajmani. She asked, how strict is the melting point of ionic liquid range? Any compound which is having a 200-degree or plus melting point, like tetrabutyl ammonium bromide, can it be called as an ionic liquid?
Yeah. Okay. So this is this is a question. You know that the definition of ionic liquid for a long time, ionic liquids were low melting salts. The person that proposed the definition of ionic liquid was Professor Ken Seddon, and this definition was completely ad hoc, which means that it just defined that below the boiling point of water, if all ionic liquids that melt below 100 degrees C, they were liquid. So this is the nomenclature that we still use today. Some people use room temperature ionic liquid to designate those that are liquid at room temperature. But in fact, I think that yes, some people call it ionic liquids. Yes, it depends on what you're using them to.
The second question from the same participant. It is what?
Professor, Samal, let me just say one thing. You're going to see that in the section that I'm going to present to you afterwards, that I'm going to use some ionic liquids that are solid, okay? But I'm going to use them in water. And people say that they are ionic liquids, okay? But in fact, they fall into the category of ionic liquids, but in fact, they are solid at room temperature. Okay, go ahead. Sorry.
Okay. So there is another same question from same participant. He's saying that it is there in the chat box also. You can also read. It's except acting as surfactants, is there any benefit of long chain cations? Because they are very viscous and are non-biodegradable.
The advantage is, for example, when you have a short chain phosphonium ionic liquid, like when you have a phosphonium or ammonium that is butyl, for tetrabutyl ammonium bromide, it is solid. But if you have long chains, they become liquid. They are very viscous, as you say, but they are liquid, and so you can work with them. Some companies even sell like phosphonium cations, what we call P6661, which is one exyl, methyl. So they are asymmetric phosphoniums, so that they are liquid at room temperature. That is the only advantage that they have. Of course, that phosphonium and ammonium ionic liquids have interesting properties, because they have their cation charge screened by the chains, while in imidazolium, the charge is open in the aromatic ring. So imidazoliums are much more charged than phosphonium and ammonium with long chains.
So we have two more queries, then we will go for the next lecture. That is one, Dr. Rupesh Verma, he asked that how can we say which compounds can form a DES?
Good question. We cannot. We cannot say. It would be very nice if we could predict, or if we could draw the solid-liquid phase diagram or predict the solid-liquid phase diagram. If we could do that, if we had melting enthalpies, at least melting enthalpies, so that we could do the ideal, just the ideal treatment, that would help us a lot. Typically, what you're looking for is compounds that could hydrogen bond. So hydrogen bonding is the key word in hypothetical solvents. And if you think that they can hydrogen bond, then perhaps they will make hypothetical solvents. But the key is really to measure the solid-liquid equilibrium.
Okay. The last question, Nikhil Kumar says, how are the DES prepared through heating method improved? You have suggested that there was impurity. How does the DES prepared through heating method is an improved one?
I didn't say it was an improved one. In fact, I said that by heating, you have to consider the three options. It really depends on what you're doing. If you're working with compounds that are sensitive to temperature, like acetates, you should not use the heating method. You should use one of the other two. When you choose to work, for instance, with the acetate anion or acetic acid, if you work with acetic acid and you use the second method with the addition of water, then when you try to evaporate the water, it is very difficult for water not to be there inside as a binding water, because you used water in the fabrication. So for this type, I would go with the grinding method. However, most people, I would say, most researchers and most papers published in this area report that they're doing by heating and mixing, probably because it is easy.
There is one more question. Can we take it or?
Yes.
Yeah, the last question. Saili Bhaviskar from YouTube, actually, she asked that can we use extraction at macro level? Can we separate the eutectic solvents from the extracted compound?
Yes, I'm going to show you in a while.
Okay, fine. So that takes care. Then maybe we move to the next lecture, if it is okay with other participants. Okay, so we can proceed, or you want to take a break? To you.
It's up to you. So I had this part, and now I have a second part. So the second part, I put everything together.
Right, then we can start. I'll suggest we can start from now. Yeah.
Okay, so let me share again my slides with you. Can you see it?
Yes. We can see the comparison slide. Yes.
Okay. So I'm going to talk to you about some applications and about the ionic liquids and the dipiothetic solvents. And as I mentioned in the title, I'm going to present two applications. I'm going to talk about the recovery, so to use dipiothetic solvents and ionic liquids in the recovery of pharmaceutical compounds, and also to use them in the vaccine production in the purification steps. So as you all know, we have the Sustainable Development Goals that were proposed by the United Nations, and we need to achieve them by 2030. And one of these Sustainable Development Goals, they are all equally important, of course, is clean water and sanitation. And so this motivated our work to study how can we clean water how can we remove micropollutants from water using these solvents that I talked to you before. Something happened with my computer. Let me adjust. Okay. 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 So when we talk about to use these solvents to clean water, we are not thinking about all the stages of the wastewater treatment plant. What we are talking about is water micropollutants. As we all know, today our water goes through the wastewater treatment plant, but when it comes to our homes, it still has a lot of pollutants that are present in very, very low concentrations, but they have a very bad effect in our health. This happens because most of the times the legislation that we still have does not take into account these micropollutants. This happens because the analytical methods that exist in these wastewater treatment plants do not go to sufficiently low limits, and so they will not detect these pharmaceutical compounds, for example, that are present in micrograms per liter, because they'll only evaluate at the level of milligrams per liter. But what we've seen is that they really impact people's health, especially children, with diseases that are irreversible. And so we need to start developing technology that can be used in treatment plants after in the effluents of wastewater treatment plants. So as an addition to the tertiary treatment that is performed in the wastewater treatment plants. Some of these micropollutants are dyes, pesticides, pharmaceuticals, nowadays plastic additives. And when I talk about plastic additives, I'm not talking about bits and pieces of plastic. I'm talking about the non-flammable compounds, the stabilizers, I'm talking about all the chemical compounds that go into the production of a plastic and that are low molecular weight and thus dissolve when we have the huge amount of plastic as we have in the ocean and in the rivers. Nowadays, we also have pathogens that we have to be aware of, and metals. Typically, pathogens are taken out with the last bleaching step. Okay. So this is water, and one of the schemes, how can I take things from water? I can either use, so I have a solvent, I can either use an hydrophobic solvent, and so the solvent does not mix with water, and so I can just perform the extraction just by contacting my solvent with water. But then I can also use hydrophilic solvents. And to use hydrophilic solvents, I have to use a strategy that is called aqueous biphasic systems. So what is an aqueous biphasic system? An aqueous biphasic system is a system of two phases that are mostly composed of water, and one of them, and this phase splitting occurs when I add to water two water miscible substances. It works as if I put one substance inside of the water, and then when I have the second substance, it steals away the solvation, the water solvation layer, and it kicks out the first compound to the second phase. So this is what I have here. I have water. I mixed inside my compounds, the two compounds, different. I have here the things that I want to separate, these little snakes. And so here I have the separation. Okay. So in terms, I'm going to show to you that this works to remove compounds from water in general. So they can be pharmaceutical compounds, but they can also be biomolecules. And for biomolecules, these aqueous biphasic systems are very nice because I can extract and concentrate a biomolecule from one phase to another. They are very easy to scale up, and they can be employed in a continuous process. And these are advantages when I use them in wastewater treatment plant. So these aqueous biphasic systems were in fact proposed quite some time ago in the 1950s, and the two substances that were used to prepare them were two polymers. And as you can imagine, this would become very viscous. And then they also use the polymer and the salt. And throughout the 20th century, there has been a lot of improvement in this technology with the use of alcohols and salts, with the use of novel polymers, the discovery of novel polymers, micelles, the integration of aqueous biphasic systems in other processes. But the true jump, let's say, in this technology came around the year 2000 with the use of ionic liquids to prepare these aqueous biphasic systems. So I can use here ionic liquids that are hydrophilic, and I can use an ionic liquid and a salt, or I can use an ionic liquid and a polymer, just to promote two phases and to separate and concentrate micropollutants and biomolecules, as I'm going to show you here today, but many other solutes from one phase to the other. In fact, I'm even going to show you that this can work with eutectic solvents. And we can prepare aqueous biphasic systems with eutectic solvents and a polymer, and eutectic solvents and a salt. Okay, so this came a little bit unformatted. So these two polymers that aqueous biphasic systems that appeared, they have advantages because they are biocompatible, because the polymers were truly biocompatible, they were biopolymers, biodegradable, very inexpensive, but they were not very much used because they are very viscous. The polymers were all more or less the same, so they have very little diversity, and they have very little diversity, so they hinder all the mass transfer operations that we are going to do. And if they are less diverse, they also have very lower selectivity. With the introduction of the ionic liquid, so I have the tailoring of the phase polarities and affinities. So we went from aqueous biphasic systems where we had, for example, PEG, polyethylene glycol, and a salt. And so I have a phase that is very concentrated in PEG, and so is hydrophobic, more hydrophobic. And I have one that is concentrated in salt and is very ionic. I go from that to smaller difference between the two phases, because instead of using a polymer, I can use an ionic liquid that already has some polarity, and so I can tune a little bit the polarity, which means that I can increase the selectivity. All this through the wide range of cations and anions combination, and they cover a wider range of hydrophilicity and hydrophobicity. So I just have to increase a little bit the chains in the cation, still keeping it hydrophilic, to change the hydrophobicity of the phase. And of course, these systems are much low viscous than the polymer-based systems. However, they are high toxicity and high price. And that is why in 2014, the first eutectic solvent-based aqueous biphasic systems were used. Of course, these are greener, cheaper, and more readily biodegradable. However, people still do not know very well how they work, and I'll talk to you about when I get there. Okay, so let's focus a little bit on pharmaceutical compounds. So our idea was to choose some pharmaceutical compounds, and we did it by looking at the European Union blacklist. And this blacklist is a list of micropollutants. It's not even compounds, it's micropollutants whose concentration needs to be very small by the year 2030. This list was first proposed in 2015, was updated in 2018, and last year it had a new update with the pharmaceutical compounds that really need to be removed from water streams and the concentration. So we focus on some of them. We focus on these non-steroid anti-inflammatory drugs, and we focus on these because these are over-the-counter drugs. And so people really use it when they have a headache, when they have a back pain. And most of them, they are metabolized, like 50% is metabolized, and the rest is excreted. And so it really ends up in our wastewater system, which does not have the capacity to retain them. Then we did the ciprofloxacin also, just to have an antibiotic that is a wide spectrum antibiotic that is very much used. Okay, so we had two approaches with these aqueous biphasic systems. We used ionic liquids, and the ionic liquids that we used are those here, as you can see. So we used imidazolium ionic liquids with these anions. So the anions are composed of sulfonate. We chose these ionic liquids because we wanted to use the aluminum sulfate salt, because this is a salt that is already used in wastewater treatment plants. It has a very low capacity of salting out, and so we had to have a somehow hydrophobic ionic liquid in order to implement separation schemes with this salt. On the other hand, we tried to go for a more green perspective, and we used the citrate salt. So citrate is fully biodegradable and compatible. And here, so we have a wider diversity of the anions. So we had the bromide and the chloride. Here we have the tosylate, and here we have the methyl sulfate. And the cations are phosphonium. Now, according to the question that somebody asked me not very long ago, if the ammonium salts, even if they are solid, can still be called ionic liquids. So here we call these ionic liquids, and some of these are solid, okay? Okay, so what we want to prepare is something like this. Here you can see the two phases in equilibrium. We are going to have, so these two phases, the majority is water, and in one, it will be water. The second most important component will be the ionic liquid and a very small amount of salt. And in the other, it will be the reverse, a lot of water, a lot of salt, little ionic liquid. So let me show you the results. So we use here, I even have a more complete set of experiments for you. This is ciprofloxacin, enrofloxacin, and amoxifloxacin, so 3 fluoroquinolones, norfloxacin, oxofloxacin, and sarafloxacin. So there are 6 here, 6 fluoroquinolones. I think that only these 4 I used for human consumption. The rest is for animal consumption. Okay. So we use this flocculant that is used in the wastewater treatment plants. We already had the phase diagrams, so we choose the composition at which we want to separate. So let me go back there. I did not talk to you about this. Okay, so here we have the phase diagrams for the aqueous biphasic systems. So our system is a ternary system, but to simplify it, we just omit the representation of water. So we just represent on one side, for instance, the ionic liquid, and on the other side, the other constituent, for instance, the salt. So here I have, then we draw the phase diagram, which is here the phase boundary between the two region and the one phase region and the two phase region. So here's my two phase region. So this is where I want to be to separate. I have to draw the tie lines. Typically, we know that the longer the tie line, the more diverse the composition of the phases are, and so the easier it is to separate. So we want to have a long tie line. And here we can see that for instance, if I prepare a solution with this composition, it will separate into two phases of this and this composition, and the ratio between the phases will be this one. If I want to have a higher ratio of the top phase, I need to move to this composition and prepare a mixture with this composition. Or on the other hand, if I want to have a higher volume of the lower phase, I need to shift to this lower composition, which means that I have more of this constituent, which is on the lower phase. Okay, so this is how it goes. So first we need to measure this phase equilibrium line, draw the tie lines, and then I choose a tie line and I choose a point to perform the separations. When we got here, all that was prepared already. So we just had to choose the tie line. We chose the longest tie line. It was a tie line of 70, which means that the ionic liquid concentration ranged between 29 and 43, and the salt, the Al2SCO4 3, 15%. And these were the results that we got. So we can see that we have some good results for some ionic liquids, almost around 100% for some of the compounds, especially those that have the tosylate anion. They are very good. Not so good for the bromine and the chloride. And so what we tried to do here was to go back and try to remove the fluoroquinolones. This is what we want to do in a cyclic approach. So we chose this ionic liquid here to perform our extractions, because this was the best one that would allow us to extract a lot and now see if we can concentrate. And so the extraction efficiency of the fluoroquinolones on average is 95%. What we know also is that the use of this salt made all our aqueous biphasic systems very acidic. So the pH was shifted 1 to 3 with these aqueous biphasic systems, which means that all our fluoroquinolones are in the protonated form. So it is very simple to devise a removal of the fluoroquinolones just by changing the pH, as I'm going to show to you in a bit. However, there is another thing that we also need to have in mind, is that the ionic liquids are very expensive. And so, as I showed to you before, we do not want to have a very high ionic liquid phase. We want to minimize the amount of ionic liquid that we use. And so we started with our extractions here. Those were the ones that I showed to you when we had almost 1-to-1. And if we want to minimize the ionic liquid phase, we have to have more citrate salt. So when I go along this tile line, shifting it to lower salt concentrations, I can minimize the amount of ionic liquid. So here I use a smaller amount of ionic liquid, like 5%, and here I'm using around 40%. And what we can see here is that the extraction efficiency does not change for when I go from this concentration of ionic liquid to this concentration of ionic liquid. And in fact, the amount of the fluoroquinolone even increases. The equilibrium, the equilibrium value, not the extraction efficiency, but the partition increases. Okay, so we are here. This is a good example on how I can keep the extraction efficiency and decrease the amount of ionic liquid that I can use. So for example, for this example that I'm showing you here, I can concentrate 13 times and here 16 times the pharmaceutical compound that I am extracting, because I have 13 times less ionic liquid and 16 times less ionic liquid. We also tried, before we extract recover the fluoroquinolones, we also had to reuse them. Can we reuse them? Here we can see that we did 4 consecutive cycles for these fluoroquinolones, and we can see that, yes, we did not even reach the capacity of these ionic liquids for the fluoroquinolones, as you can see here. So we can reuse them. So they have a high capacity for fluoroquinolones. Now, how am I going to remove the How am I going to remove the N-state compounds from these systems? So in the first case, I use the exchange of pH, because fluoroquinolones are positive at very low pH, neutral at pH 7, and negative at pH above 7. So what we did is we put the pH at pH 7, and what happens is that fluoroquinolones are no longer soluble in the ionic liquid phase. And so they will all desorb from the ionic liquid phase to the water phase. And so we can concentrate them. In the case of NSAIDs, since they do not have pKa's, what we used, it was the precipitation. So what we did was, so for NSAIDs here we have the extractions, we chose this one, and what we did, my slides are all out of place, I'm sorry. What we did for the NSAIDs was to use water to precipitate them. So I have here all the NSAIDs precipitated. So I took out, this is the ionic liquid rich phase. I took out the ionic liquid rich phase, I added water. The NSAIDs are not very soluble in water. I filtered, they precipitated all, and I can recycle again my ionic liquid to the aqueous biphasic system. For the fluoroquinolones, here we have. So for the fluoroquinolones, I had water, and this is the ionic liquid. I had water and the salt. I make the extraction. This is the ionic liquid rich phase with fluoroquinolones precipitate. because of the change of the pH. I adjust again the pH, and I recycle again my ionic liquid rich phase. Okay? So in both cases, in case of fluoroquinolone, by exchanging pH and making it less ionic, I could recover them. In the case of NSAIDs, I use their low solubility in water to precipitate them and recover them. And in the end, in the two cases, I was able to recycle the ionic liquid rich phase back again to my system. Okay, so here I have what I was telling you before. So I have the water and the ionic liquid phase. The ionic liquid rich phase is separated, the salt is recycled. And here I have water in the case of the NSAIDs precipitate and are taken out. And the ionic liquid solution with water is dried. The water is recycled back again here, and the ionic liquid rich phase is recycled to the beginning of our system. And so this makes it a system that is truly circular. And so I don't need to invest a lot in an ionic liquid, only in the beginning, and then the rest of the time, I just have to reuse it. Okay. Now I'm going to show to you, I showed to you what we have done with ionic liquids. To work with ionic liquids that are hydrophobic, it was not possible to extract micropollutants from water, because most of ionic liquids that are hydrophobic, they are still a little bit soluble in water. And so when I contact them with water, still 10% of ionic liquid remains in water. And so this is not feasible, because then I would damage the water even more. And now the water does not have micropollutants anymore, but it has ionic liquid. So in ionic liquids, the case to work in the wastewater system was to use aqueous biphasic. In here, this is an example that I'm going to give to you about the eutectic solvents. Again, I think that can you hear me?
Yes, we can hear you.
Can you see my screen?
The full screen is not there. Yes. We are looking at the slide extraction of bisphenol.
Okay. 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 So I don't know what happened, but it looks like my presentation, some slides just are missing. Okay, so now I'm talking to you about the extraction of other micropollutants with eutectic solvents. So we have prepared a lot of eutectic solvents. Let me just check if these slides are not far below, because I really needed to show to you here now the slides. I don't know where the slides went. Okay. So I'm sorry for this, but now I'm going to show you, I'm going to talk to you a little bit about the eutectic solvents. So there are a couple of slides that are missing here. What I wanted to tell you is that most of the slides that I've showed you on eutectic solvents talk about hydrophilic eutectic solvents. And hydrophilic eutectic solvents cannot be used in water, because otherwise I would lose my hydrophilic eutectic solvents to water. Again, think also that what I told you before, that eutectic solvents are mixtures. And so when I put them in water, I do not have the same thing as it happens when I have one ionic liquid in water. When I put an ionic liquid in water, I have one compound in water. When I put an ionic diplothetic solvent in water, I have a mixture of the two compounds in water. What happens if I, as I told you before, I can have a wide variety of compounds? I'm going to go upstairs so that I can better explain. There are a couple of slides missing here. Okay. When I have two compounds, when I have the diplothetic solvent. So when I put them in water, remember, the most important thing in diplothetic solvents are hydrogen bonding. And so if I put them in water, water is the compound that most hydrogen bonds. And so water is going to solvate individually these two compounds. And what I'm going to get is a solution of the two compounds inside of water. So I can have a couple of behaviors here. I can have, what about if I mix two hydrophilic ionic liquids, they will both dissolve in water. If I put two hydrophobic ionic liquids, none of them will dissolve in water, and I will have a liquid-liquid equilibrium. What happens when I have one hydrophilic compound and one hydrophobic compound? In that case, I'm going to have phase separation also. I'll have my hydrophobic compound on top, and then the hydrophilic compound is going to partition between water and the phase composed of the hydrophobic component of the diplothetic. So be very careful when you use or when you think about eutectic mixtures to use them in water, or for example, the reverse is true if you think about of using them in n-hexane. In n-hexane, the hydrophobic part of the eutectic mixture will be mixed, and you will end up with two phases with the hydrophilic compound and the hexane with the hydrophobic component inside of it. We have to be very aware of this. I have some very beautiful slides that I don't know where they went, but to show you the diplothetic solvents that we prepare. However, they're not here. And so I'm going to explain to you. So we prepared the hydrophobic diplothetic solvents. And hydrophobic diplothetic solvents, as I told you before, they have to be made with two hydrophobic compounds. If you mix one hydrophobic compound and one hydrophilic compound, the hydrophilic compound will go to water. So we used a natural compound, which is DL menthol, as you can see here. Menthol had been used, and it is still used a lot in the pharmaceutical industry, and we used the fatty acid. So we formulated these diplothetic solvents that in fact are not very deep, because neither menthol nor C8 have very high melting points, and the working window that I get is not very large, but still it is considerable because both of them are solid at room temperature. So in this work here, we prepared hydrophobic compounds based on menthol and fatty acids to remove pesticides from water. And as you can see here, this result is quite different from the other ones that I showed you before. Because here I have an hydrophilic, I have an hydrophobic compound, and I don't have any salt. So the extraction efficiencies are okay for imidacloprid and acetamiprid, but for the other pesticides, they are not very good. Pesticides are probably the most difficult compounds to extract from water. And so we really need to be very careful when we use pesticides. here we can see that we can reuse the compound. So exactly in the same way that we can reuse the ionic liquid systems above, here we can also reuse the eutectic solvents. Realize, however, in the example that I gave you before, we did not lose extraction efficiency, and here we lose extraction efficiency when we reuse 4 times these eutectic solvents. The novelty here is really to use compounds from renewable resources, natural compounds, that are completely hydrophobic and do not leach to water to perform these extractions. We did some other works, and here you can see that we have different eutectic solvents. So these eutectic solvents that I have here are composed of a sodium salt with long alkyl chains so that it does not leach to water, and again fatty acids. Here in the end, we compare the efficiency of these deep eutectic solvents with salts with the all natural deep eutectic solvents. As you can see, the compound that has the highest extraction efficiency is unfortunately one of these compounds that has a long alkyl chain ammonium salt with bromine. However, these results are still very interesting, especially this with D-L-menthol and C10, because it leads to very high extraction efficiencies. And so in terms of using it to recover bisphenol A from water, bisphenol A is a plasticizer from plastic bottles, water plastic bottles. Perhaps it is much better and cheaper to use D-L-menthol than this deep eutectic solvent. Here is the computational optimization that we have done. So these are results that are optimized, and we use a very low amount of D-L-menthol, and we can extract 95% of bisphenol A. Okay. Then we decided to, this is the optimization, and the optimization that we did, it was the contact time, and we realized that this extraction was happened very quickly. And so we thought that this system could probably move to a different stage. We could do a different thing with this system just because it has a very fast kinetics, either in one or in the other eutectics. So either with the best one or the other one. And so this is the optimization of the heating rate and the ratio of dash to water. And so what we decided to do was to support these hydrophobic deep eutectic solvents. So what we did, it was to use a porous support, and we support the 2 deep eutectic solvents. In fact, and then we cut all this big membrane in small membranes and use it to extract. So what have we done? What we've done is we have created an adsorption material based on the hydrophobic deep eutectic solvent, and what we are counting on is on the nano effect, because this membrane has very small pores, so it is as if we are creating micro droplets or nano droplets of our solvent that have a much larger surface area, and thus will allow us to, for instance, faster remove the solvent, to recover it just by filtration, to reuse it also. And so here we can compare the effect of mass. For example, here we used 4 milligrams of mass. When we do the liquid-liquid extraction, we use 2 grams of solvent. Here we use 4 milligrams. And we see that we can achieve almost 90% with just 4 milligrams. And with 15 milligrams, we can achieve 95%, which is almost the same thing that we did with the liquid with 2 grams. Here is the reuse. It's highly reusable when it is implemented in the adsorption material form. And here is the extraction efficiency of liquid-liquid versus the adsorption process, taking into account that the adsorption process was carried out with 0.05 milligrams. So here. No, I'm sorry. 0.5 here, okay? So what we can see is that for this solvent, they are pretty much the same. In fact, for all the solvents, they are pretty much the same, the extraction efficiency. But with this, with the development of this supported gas membrane, we can save on the amount of eutectic solvents that we need and more easily recover and reuse the material. Okay. So this was bisphenol A. Now we pass to ciprofloxacin. Ciprofloxacin, we are going to use the trick that we used for ionic liquids above. So we are going to do an exchange of pH. First of all, we just screen the extractions with all the hydrophobic eutectic solvents. We were able to see that in this case, all those that were ionic, that had salts in it, performed very bad. And the neutral ones performed much better, which means that we also did the pH, 3 pHs, and we saw that ciprofloxacin is better extracted in the anionic form, even for neutral compounds. And so, and we looking, if we were searching for the extraction mechanism, we measured the solubility, the water solubility inside of the eutectic solvents. So the eutectics are not soluble in water, but water is soluble in eutectics. And what we can see here is that, for instance, those that are ionic can, when you contact them in water, can easily gain 5% weight percent of water, which is, as we have seen before, like 35% in terms of moles. However, these eutectics that are neutral, based on menthol and fatty acids, or only fatty acids, do not have much water, and so remain much more hydrophobic, and this is why they can extract much better the ciprofloxacin. This is why ciprofloxacin is much more soluble in neutral eutectic solvents. It is because they are more hydrophobic than ionic hydrophobic eutectic solvents. Here is the reutilization. Here is the reutilization of ciprofloxacin. So we have 4 cycles here. We did 4 cycles. You can see that ciprofloxacin is much easier to work than the pesticides, that the pesticides, the recycling efficiency was decreasing with the number of the cycle. Here, it is decreasing a little bit in the 5th cycle, but then we can clean the eutectic solvent using activated carbon. Here we separate the 2 phases. This is the activated carbon, this is the clean dash, and we can recycle it again, and we recover the extraction efficiency of the first step. So this is what I want here. I don't know what I've done with this presentation. Here, the ciprofloxacin recovery is done exactly in the same way as we have done it for as we have done it for the aqueous biphasic systems with ionic liquids. We do it by change in the pH, and so the ciprofloxacin does not have as much affinity for the dipiothetic solvent phase and leaches to the other phase. Now I'm just going to go briefly over the second example that I have here, which is the use of these ionic liquids and dipiothetic solvents to develop vaccines. So it is the third sustainable development goal that we are now addressing, good health. I took this slide from one of my students, but I think that right now I do not need to tell you how important it is for us to have good vaccines, to develop vaccines quickly, and to have good separation and purification steps that allow us to purify and to these types of separations. If these would have been developed, I'm sure that we would have vaccines by now. The downstream processing of vaccines, as you all know, costs around 50–60% of the entire, here it is, virus and virus-like particles, 50–80% of the entire production cost. And typically they are very complex and they take a long time. And so these are really in need. I'm going to show you two examples of aqueous biphasic systems for the extraction and purification of virus-like particles. So we had, we prepared virus-like particles from okay. I cannot remember the disease. So we prepared virus-like particles, and the important thing in these virus-like particles is that they are sterile, which means that they do not have the RNA, so they are virus-like. They are not virus particles. They are non-contagious. They just have the same shell and of those that will be carried out in the vaccines, but they are non-infective. And so we are going to use ionic liquids, and we are going to use natural dipiothetic solvents. The concerns are very different when we want to extract micropollutants from wastewater stream effluents, and when we want to extract virus-like particles. Because all these compounds have to be approved by the FDA, otherwise they cannot be used in the extraction of pharmaceutical products. So although the first one is a more academic study, because as you're going to see, the ionic liquids that we use can be toxic. The second one is really a purification system that could be implemented because it uses natural dipiothetic solvents based on carbohydrates, so sugars. Okay, so what we did here was to prepare quaternary aqueous biphasic systems. How come quaternary? So in the ionic liquids, what we've done is we use the salt, an ionic a salt and PEG, which is the traditional systems that are used for virus purifications. And then we added an ionic liquid as an adjuvant. So what is the advantage of this? The advantage is that adjuvants are typically present in a very small concentration, and so we overcome partially the toxicity. In the second example, we use natural dipiothetic solvents and polyethylene glycol. What happens is that this dipiothetic solvent in water, it breaks down into its compounds. And so I'm going to have 3 compounds in solution, okay? These nuts are made of 2 carbohydrates, and so I will have the 2 carbohydrates in solution plus the PEG. In the first one, I will have the salt, the ionic liquid, and the PEG. Okay. And so we studied all this. My student did this in high throughput liquid handling station, and so he just had to fill all the wells, the micro wells, the 96 well plates with different mixtures, and then set it there for the system to read and to analyze the systems. So typically he used 100 microliter samples, either to the new aqueous biphasic systems, to prepare new aqueous biphasic systems, and then the reading plate will centrifuge and sample, dilute, and do the analytics. Okay, so here we studied all the traditional things. We started the increase in the PEG molecular weight for 3 salts: citrate, sulfate, and phosphate. We have here plotted the extraction efficiency and the yield. So as we can see, as the molecular weight increases, of the PEG increases, the recovery yield decreases in all of them. And we can also see that the citrate is typically more favorable. It yields better extraction efficiencies and yields than the other 2 salts. And so this is what we chose. We chose to work, okay, so we chose to work with PEG 400 and the citrate salt. Here we tested the pH. We can easily see that pH 7 is the best one to work. And so we are going to use a buffer, a citrate buffer at pH 7. And here are the extraction efficiencies of the VLPs. So here we have several tie lines. We chose these points here. We prepared the mixtures with these points here. And the phases are these here. And as you can see here, we have a very high extraction efficiency for the tie line 40, where we have a recovery yield around 90 and an extraction efficiency also around 90. And so this is what we are going to choose. After all this has been optimized, we decided to use ionic liquids as adjuvants just to see if they would help to reach the 100% extraction efficiency. So we used imidazoliums, we used ammoniums, and here we use imidazoliums with different anions. So let's see what happens. So I have 5% of each one of the ionic liquids. This we established as our maximum. So we saw that when we increase the alkyl chain of the cation, we didn't increase in comparison with no ionic liquid. No ionic liquid, in fact, had better results than when we put ionic liquid in there. Again, when we have no ionic liquid, we have better results than when we have the ammonium salts. So this is the imidazolium, these are the ammonium. However, we have here a very interesting result. So we have an extraction efficiency that is slightly higher for the imidazolium, for that imidazolium cation, the C4-min. And here also we have an extraction efficiency that is slightly higher than with no ionic liquid. So these are the 2 basic results that we got from there. In what concerns the anion, here we are slightly better because we have one extraction efficiency that is slightly better than with no ionic liquid, and that corresponds to the acetate anion. And so probably the acetate, the interaction of the VLPs with the ionic liquid is made through hydrogen bonds. And we saw that this ionic liquid in particular, the C4-NIM acetate, has the highest capacity to donate hydrogen bonds. So it shows this ionic liquid. Now we know that we have high extraction yields, but how does our VLP behave? How are the structural properties of the extracted VLP? For that purpose, we use the zetasizer in order to see if the VLPs were aggregated. And here we can see that for these two systems, the VLP were aggregated, so they had aggregates in this size, so large. And we can see that we can also see that in the salt-rich phase, the VLPs are not very stable. They have also aggregates in a very large size. But in the ionic liquid-rich phase, we can see that for some of these systems, no aggregates are formed. On the other hand, we also performed flow cytometry with HUH7 cells infected in order to see if our VLPs were contagious or not. So these were prepared as contagious, and they were tested to see if they would remain contagious after being treated with, being separated with our ionic liquid. So what we can see here is that, so this is fluorescence. We can see that for acetate, we have nice fluorescence, which means that yes, they are working. And here also we have nice fluorescence, which means that yes, they are working. So these are very good results. Now, finally, just to conclude this work, we used cell culture supernatant. This was all done in water. Now we suppose that our VLPs were not purified, pre-purified. We use them as they were prepared from animal cells. And this is a chromatogram of the PEG-rich phase. This is a chromatogram of the salt-rich phase. These are the VLPs. These are the impurities. These are the VLPs. These are the impurities. We can see that we do not have VLPs here. And we can see that we have here a very big peak and the impurities here also. Okay, so this is, we have some impurities in the same phase of the VLPs, which means that everything is going to the ionic liquid phase. However, when we calculate the impurities and we treated this chromatogram, what we saw is that, yes, for acetate, the purity of the VLPs is only 40%. So we extract a lot, like 90%, but the purity is low. But if we use the chloride, we can have a purity of 70%, which means that sometimes we have to look both of the extraction efficiency, if I extract a lot, and now here if they are selective or not. So these are very good results because the systems that are used without ionic liquids have a purity of 32%. And here with ionic liquids, we managed to get 70%. So this was a very nice step forward in the direction of the development of a selective method for purification of VLPs. Okay, so now, last but not least, I just want to show you the second case study on aqueous biphasic systems and natural eutectic solvents. So what we're going to try to do is things similar to honey. And what we are going to try to do, so it's binary NADH, eutectic solvents, with glucose and sucrose, and glucose and fructose, and sucrose and fructose, and with 3 sugars here. We have a ternary. So when you try to do this, this is honey, this is very viscous, and when you put it in water, of course, that everything dissociates, because as you saw before, the concentration of the natural eutectic solvents is low, and so water is more than 50%, and so we are in those regimes where all the compounds are separated. So here, in fact, although we did the deep eutectic solvents, in fact, we tested preparing the deep eutectic solvents and putting them in water and just putting the carbohydrates in water, and the results were the same. Okay, so we have here a cytotoxicity of these deep eutectic solvents in the cells that produce the VLPs. I remember now the VLPs were for what? They were for hepatitis, to develop a vaccine for hepatitis. What we can see here is that, for instance, there are some deep eutectic solvents that have a very nice cell viability until a high concentration, 20%, like for instance this, fructose and sucrose. But there are others that, like glucose and sucrose, that really do not make it viable. And the same thing here. So these cells are even more sensitive to the presence of the osmolytes. And so in very low concentrations, they are all tolerated. But if we increase a little bit the concentration, like fructose and glucose seems to be the one that is working the best. So here we did all the phase diagrams, as you can see from here. So this is the two-phase region. This is the one-phase region. We can see that we can tune, like for instance, when we have just one carbohydrate, fructose, glucose, sucrose. We have here fructose and glucose, which is very different from sucrose. And we can tune the two-phase region just by the addition of 1 or 2 carbohydrates. So now I'm going to perform the VLP extractions. I'm going to use 20% of carbohydrates, okay, and 100 microliters of purified VLPs. And we can see here the extraction efficiencies. So we can see that we had very high extraction efficiencies for the other phase, and only one was capable of, or only one, it was in fact just sucrose, was able to extract it to the other phase. So we choose this deep eutectic solvent to separate. And now here we are going to see the purification. So this was merely the extraction, and this is the purification. So we use BSA, which is bovine serum albumin, as contaminant. And we can see here again that we changed, we have a very high purification also for the fructose, glucose, and that sucrose no longer brings the VLP to the hydrocarbon phase, but it brings VLP to the other phase. Okay, so this is the selectivity. These are the K values and the extraction efficiency, and this is the selectivity. And so we can see that fructose glucose is the one that is more selective. And so what we are going to do is aqueous biphasic systems composed of PPG and fructose and glucose. Okay, and this calls the attention for the extraction efficiency and the selectivity. Again, we've done the structural properties, and we can see that there are some VLP flocculation in the presence of the osmolytes. Most of them have high average particle size, either in the bottom phase with fructose, sucrose, and with glucose sucrose. So these are, here we still have to do some little bit of work. So now, just to sum up, so what are the challenges? The challenge, of course, is I was asked before, is the development of the recovery step. The recovery step is always the most challenging, and the purification also. Because as you all know, ionic liquids, they dissolve everything. You can tune the properties to have 100% extraction efficiency, but then it is very difficult to desorb compounds from the phases. For example, in this case, what we were aiming was not to recover the VLPs. Since fructose and glucose are osmolites, which means that are compounds that are present in cells, that we could formulate the vaccine with the carbohydrates, the carbohydrates also. So in this way, we avoided the separation. To recycle the compounds that we use to prepare our systems. So we want to recover the compounds that we separate, but we truly want to recycle the phase-forming chemicals also. Then we have the problems of scaling up. The aqueous biphasic systems can be scaled up. The liquid-liquid extraction also can be scaled up into a continuous mode. However, we need to think about other clever solutions, as I showed you here, like adsorption, that are much more economic and still have the same extraction efficiency and partition. And then, of course, we need to start integrating. Most of the times, these technologies using deep eutectic solvents and ionic liquids are still tested alone, and we need to start understanding what is the effect, how are they effective when they are integrated inside of a process. So, which means more collaboration with other people. And this is all for you. Thank you very much for your attention. I'm sorry that I did not have 6 or 7 slides in the middle.
Okay, thank you. Yeah, it was. We come to the end of Professor Maruko's lectures. So now the forum is open for any questions from the participants. They can put their hand symbol, because I did not find any questions in the YouTube link. So the participants, any question you want to ask? So maybe, I don't know, they may be very tired or something.
I think they are. I think they are. Probably should have made an interval.
Yeah, maybe, yeah, that's true. But anyway, if you have any questions, you are free to email your queries to Professor Maruko. Yes. She might take that up later. So
yes.
Once again,
I will answer everyone.
Yes. So again, I'd like to thank Professor Maruko for giving us a wide range of activities related to ionic liquids and deep eutectic solvents. And you had touched upon various applications, starting from the pesticides and then finally ending with virus-like particles. So I hope the participants, you might have got an idea of where are likely to be used. And we have some more interesting lectures from tomorrow. She will be talking about the polyionic liquids for carbon dioxide separation and also as sensors for solid phase micro extraction. So we will join then again, back to thank Professor Maruko, and we will join again tomorrow. Okay. Okay, there's something, some comment has come. Let me see. Just a second. Let me check. No, there is nothing.
Okay.
No, there's no comment. Yeah. I have just one comment. This one. When you extract this ciprofloxacin, you said that with the increase in the organic acid, the extraction keeps on increasing, right? So it means that if we go on further, so the extraction will be only controlled by the entropic part, because they have very long chains, right? The viscosity will also increase. So any way where can we stop somewhere in between, or how do you decide this chain length?
In fact, we stopped there because at the time we were interested. This was one of our first works with fatty acids, and we just chose these 3 ones because they are those that are solid at room temperature. When we go to C12, it is already liquid. It does not mean that it does not form an eutectic, because it forms an eutectic, but we do not gain much in terms of the liquid window. But I think it is a very good question, and perhaps it can be very useful in order to enhance the extraction efficiency of ciprofloxacin. Yes, I think it is a good idea.
Okay, sure. So we'll have more questions and more discussion tomorrow. Again, thank Professor Maluko. So the participants, we meet tomorrow at 6 o'clock Indian Standard Time. Okay, please be kindly join in the same Teams link which I have circulated. Thank you.
Thank you so much. Thank you, and tomorrow. Bye bye.
Bye bye.